All right, picking back up right where we left off. We're going to finish up chapter 6 here, looking at ossification, bone growth, or the formation of new bone, and how our skeletal system plays a role in mineral regulation for the body. So we have two major types of ossification, which in some cases is referring to the formation of new bone, and in some cases is just generally talking about bone growth, though we do have a separation here in the text. So ossification, referring to forming new bones. We'll then talk about two different ways that bone grows after it's been formed, so increases in diameter or increases in length. But ossification is talking about new bone, forming new bones. We have two types. The first being endochondral. So if we break this word apart, chondral referring to chondrocytes or cartilage, endo referring to inside. So endochondral ossification is forming new bone from within cartilage. And so this is mainly how our long bones are formed, our new long bones get created. And so they start out as cartilage, making essentially the model, the general shape for what that bone will eventually become. Okay? So a cartilage model, and then we get bone kind of penetrating in and then forming from the inside, replacing all of that cartilage with bone cells, hydroxyapatite crystals, and collagen fibers. And a result of that growth and the organization, or I guess the different stages that we see here, ends up leaving us with a thin line of cartilage that takes longer to replace than the rest of it. And we call those our growth plates, or the epiphyseal growth plates. And so in maturing children or adolescents, if you look at an X-ray, you would still see those little regions of cartilage that have yet to be replaced by bone. But then in a fully mature adult, all that cartilage should have been fully replaced by bone. But we'll look at all the stages of it here. So again, endochondral ossification. We are making bone from within a cartilage model. And so we start with this cartilage model, generally in the shape of what is going to become our long bone. And so the first part of this is we get essentially penetration of the blood vessels into the center of this cartilage model that is going to start supplying all of the osteoblasts and osteoprogenitors and osteoclasts. Right? We're going to have all of our bone cell types showing up here as they start forming, breaking down the chondrocytes and the matrix of the cartilage and replacing it with bone cartilage, with bone matrix, right? Replacing it with hydroxyapatite and collagen fibers. So we get our primary penetration into the diaphysis, so into the center, the long part, the shaft of the bone. You see that here. And so this becomes our primary ossification center. So where bone growth is starting first, primary ossification. And so you will have osteoclasts breaking down these chondrocytes that have enlarged and died off. And then osteoblasts replacing that space or filling that new space with collagen fibers and hydroxyapatite crystals. And so it's this constant cycle of osteoclasts breaking things apart and osteoblasts replacing that space with bone as we get that to start growing and filling. And then osteoclasts will break down the bone that was there before, allowing this to continue expanding outward and outward and outward, leaving behind this large space that will become the marrow cavity of the diaphysis. Until eventually we get a perimeter that is basically all made up of compact bone. So next, we get penetration into both of the epiphyses. So those blood vessels that supply are going to spread into each of the epiphyses, and these become secondary ossification sites. So now we're going to have new bone growth from the center of each of these epiphyses. In the metaphysis, or metaphyses for both of them, which is this space, this layer of cartilage in between the diaphysis and both of the epiphyses, that metaphysis doesn't get broken down as quickly. This is going to end up lasting much longer in what becomes that epiphyseal growth plate that you see staying behind as a child matures into a fully mature adult that will eventually then be replaced by bone. But anyways, our secondary ossification sites, we get the same general pattern happening: osteoclast breaking things down, osteoblast replacing that with bone, until eventually we have a space that allows room for spongy bone to now go in and grow. And so that is how we make our long bones, or at least make the original shape of long bone. Starts with a cartilage model, and then all that cartilage gets replaced with bone, starting with our primary ossification center in the diaphysis, and then spreading out and penetrating into the two epiphyses for our secondary ossification centers, where we replace cartilage with bone. Most of the epiphysis is going to stay empty as far as there's very little spongy bone filling that space because most of it is going to be full up with marrow. But the epiphyses are each going to quickly end up full of spongy bone. So there will also be bone marrow in those epiphyses, but we have spongy bone taking up a lot of that space, a lot of the volume. And so by the end, you have this essential setup with all of this blood supply going throughout it. So we have our original penetration that made our primary ossification center. So we have blood vessels coming through here, and then we have blood vessels going into each of our secondary ossification centers there, and then spreading throughout all these central canals and the compact bone, or in this space. And so the specifics of the epiphyseal growth plate, I'm not going to assess you on as far as in our unit exams. But if you want to learn more about it, check out this video or some of the other suggested videos. But eventually that epiphyseal growth plate, which again is what was left at our metaphysis here, will be replaced by bone. But as you can see, if you take a X-ray of a still maturing human, you would end up seeing what looks like little gaps in spaces in between each of their bones. Like these bones are floating in space within their hand here. But that is just cartilage left over, right? These bones, these metacarpals that we're looking at here and their little carpal connections just haven't fully developed yet. They haven't been fully replaced. So if we look at a fully formed adult, right, we don't have nearly as much of those spaces. You can see all those hydroxyapatite crystals of the bone showing up here. So X-rays are great because they can penetrate through all of the organic matter, right? Basically ignoring all of your actual cells, all of your carbon-based molecules, your organelles, etc., and are just showing us a reflection of the inorganic matter, which is going to be our bone. Right? So we get to see our bone. But that's why those spaces show up, because those chondrocytes and the cartilage matrix is mainly organic matter. So that ends up looking like these empty spaces, whereas bone is mainly minerals, hydroxyapatite, inorganic matter. Okay. So looking at now bone growth. So after a bone has been formed, how does it continue to grow? So to lengthen or increase in diameter. You may see bone growth being referred to as ossification, but as far as how our textbook has referred to it, ossification is talking about making new bone, and then bone growth is a separate category. So we've only talked about one type of ossification, but since that is looking at long bones, it then goes on to talk about the growth of long bones. So that's why we're getting this little aside here. But essentially, after a bone has been formed, after it has been ossified, it can grow through interstitial growth to increase its length and appositional growth to increase its diameter. So both of these have a little bit of remodeling or recycling to them, but that appositional growth is mainly remodeling. So osteoclast breaking down old bone and replacing it, and osteoblast replacing it, which is going to end up making it denser, more compact, and increase that diameter or thickness. So that is appositional growth, which would be in the periosteum. Then interstitial growth, where new bone tissue is forming in our diaphysis, that's going to push these epiphyses farther from each other. So interstitial is going to be between our epiphyses, pushing those epiphyses farther away from each other, so lengthening the bone, more and more bone tissue, allowing that diaphysis to grow in length, the shaft to grow in length. And then apositional growth is going to be in the periosteum, so all the way around the outer membrane here, which is going to remodel bone, making it more and more compact and dense, increasing the thickness of that bone, so making it more structurally secure, I suppose, in that case. So interstitial for length, apositional for thickness. And now on to our second type of ossification, so how we make our dermal or our flat bones. So intramembranous. So instead of being endochondrial, so within cartilage, intramembranous is between our membranes or inside the membranes. And so this is going to be forming most our flat bones. And this comes from the dermis. So instead of having a cartilage model for our bone cells to penetrate into and then start breaking down and replacing, this is going to be the formation of bone cells from the dermis that starts spreading into this space deep to the dermis, ultimately forming a new flat bone, a dermal bone. So we don't have a cartilaginous model. We're just getting bone growth from the dermis. So let's take a look at that. Oh gosh, I didn't realize the quality of this looks so low. But bear with me as we get through this. Essentially, from within the dermis, we're going to end up getting these ossification centers surrounded by osteoprogenitor cells that are going to make osteoblasts, and osteoblasts are going to start producing collagen and hydroxyapatite crystals, and that's going to start filling up all this space, this mesenchymal dermal connective tissue. It's going to replace all of that with bone. So these little ossification centers are going to start enlarging and end up forming these like branches as they do so that we call spicules in their immature form. So ossification centers start to spread out as more and more collagen and hydroxyapatite crystals are being deposited. And so they create these little branches, these spicules. And over time, those spicules will end up connecting with each other. They run into these little canals of blood vessels, and they don't break those blood vessels down. So that just ends up becoming a structure that the bone forms around. Okay? Until eventually, all these spicules are what become our trabeculae. And those spaces stay there, allowing for room for those blood vessels to go through each of those trabeculae, right, within that space. And so now we have spongy bone, filling up most of this inner portion with layers of compact bone going around the outside. And this is what makes our flat bone, our spongy bone sandwiches. And so compact bone making up the layer just deep to the periosteum, and then spongy bone mainly making up that inner portion with their trabeculae. There's not much more to it than that. And so lastly, when you talk about our skeletal system's role in mineral regulation for the body. So just looking at the composition of bone itself, again, a majority of the mass is inorganic. It's mainly these hydroxyapatite crystals. So 67% of the composition of your bone is just minerals. Only 33% comes from our organic compounds, and most of that is coming from the collagen. So there's very little of the mass of our bone that's coming from cells. It's mostly the matrix, the collagen fibers, and then the inorganic minerals, the hydroxyapatite crystals, taking up that space. And so looking at those hydroxyapatite crystals, they are mostly calcium and phosphate, which are both very, very important minerals. I guess phosphate is more than just the phosphorus mineral, as these are phosphorus with oxygens making up those molecules, but still inorganic. Calcium is very, very important for a lot of our nervous system activity, for action potentials and the release of neurotransmitters between neurons. Calcium does a lot of regulating that. It's very important for our muscle contractions, as we'll see in future chapters. Phosphate is really important for energy. right? ATP and GTP, the P in ATP is from phosphate, and phosphate bonds, holding each other to each other, are what provide the energy for cells to do work. So having somewhere to store and release phosphate from is really important. But we also have a few other minerals stored here. Some potassium, some sodium, some magnesium, and then some carbonate are all found as a part of that hydroxyapatite structure. And so that's what makes up bone itself. And now if we look at how much of the concentration of these minerals in our body are found in bone, you can see how much we are using these bones as a storage system, or as a bank for these things, like where we deposit them when we have extra, and then we withdraw from it when we need more in our blood to access for our cells. So 99% of the calcium in your body is found in your bone. So whenever you have extra calcium, that is all being stored basically in your bone. And when you need access to more calcium, you don't have enough traveling in your blood, we break down our bones to get access to it. And so same could be said for phosphate, where 88% of the free phosphate in your body is in your bone. 50% of the magnesium and 35% of the sodium is found in your bone. So we are constantly balancing and regulating, right? With osteoblasts taking calcium, phosphate, magnesium, sodium from the blood and storing it in our bone when we have excess. And then osteoclasts coming around and breaking apart that bone in order to release more calcium, phosphate, magnesium, and sodium into our blood if we need it. And there's a variety of hormones playing a role in that balance. So this is mostly a reference slide for you. The arrows that I have added to this table from the text are showing the impact of that hormone on blood calcium levels. So everything with a blue arrow pointing up would increase the amount of calcium in our blood, which means they're either taking that calcium from our blood or from our bone, or helping with getting it from our food, right, through our digestion and absorption. And then everything with a red arrow is going to decrease blood calcium levels. So either depositing calcium into our bone or increasing how much of it we are excreting from our blood, like from our kidneys. And so the main ones to be aware of are going to be parathyroid hormone, PTH, calcitriol, and then calcitonin. So we'll come through that. So parathyroid hormone and calcitriol are mainly acting as factors that increase blood calcium levels. So if we need more calcium in the blood, so again, helpful for muscle contractions, helpful for the release of neurotransmitters in our neurons. So we do need regular access to at least 8.5 milligrams per deciliter in our blood. So whenever blood calcium levels are getting below this range, our glands and different organs in our body, different tissues in our body are releasing parathyroid hormone and calcitriol. Calcitriol is the mature version of vitamin D, what we typically call vitamin D. So parathyroid hormone with some assistance from calcitriol is going to help with increasing absorption of calcium from our digestive system. In fact, without parathyroid hormone and vitamin D, the transport proteins that are going to move that are supposed to move calcium out of our intestinal lumens and into our cells and then into the bloodstream, they don't work without vitamin D and parathyroid hormone there. These things activate those transport proteins to get them across the membrane and into our actual body, out of the intestinal lumen. Parathyroid hormone is also going to trigger our kidneys to retain calcium ions rather than excreting it as waste, adding it to our urine. And parathyroid hormone is also going to activate osteoclasts, right? So that we can start breaking down some of our stored calcium in our bone to get more into our blood. So we have three different methods of regulating calcium. Increasing absorption or decreasing absorption from our intestines, so from our digestive system. Either excreting or retaining calcium through our kidneys, and then either storing or releasing calcium from our blood. So parathyroid hormone is going to help get more calcium by acting on all three of these, and then vitamin D assists with parathyroid hormone with that digestive function. So again, increasing absorption from our digestive system, retaining calcium, so not excreting it as waste, and then increasing osteoclast activity to help break apart our bones. And that all is stimulated by this 8.5 milligram per deciliter concentration. So typically, if our calcium concentration gets below that in our blood, all three of these are going to activate. And so on the opposite end, if we have excess calcium, so if we are getting above a 11 milligram per deciliter concentration, our body is going to start signaling our different tissues to store that calcium or get rid of it, to not end up impacting the pH of our blood too much. And so we can do this by decreasing parathyroid hormone and calcitriol to stop the activation of those transport proteins. So stop getting calcium from our digestive system and let it go all the way to be excreted as our feces. We can release a different hormone called calcitonin, which is going to allow for calcium loss from our kidneys, and it is going to block osteoclasts, which allow for just those osteoblasts to start taking calcium from the blood and putting that into our bones. So not necessarily activating osteoblast activity or stimulating osteoblast activity. Osteoblasts are continuously active. It's just we regulate the bone part of this by either activating or inhibiting osteoclasts. So parathyroid hormone activates or stimulates these osteoclasts, and then calcitonin inhibits them. So if we need to get calcium out of our blood, we can put that into our bone through osteoblasts. We can remove it from our body via our kidneys, getting it out of our blood, and then we can just stop absorbing more of it from our digestive system by decreasing the amount of parathyroid hormone and vitamin D that is traveling through our blood. And so altogether, that is how our bone assists in regulating the concentrations of these minerals. So think back to when we were talking about vitamin D and our skin and how important it is to make sure you are supplementing vitamin D if you're not getting access to UV rays from the sun, which we don't here in Seattle for at least 6 months out of the year. And so without that vitamin D, you may not be able to absorb calcium from your digestive system and thus get it into your bone. And so if you aren't getting calcium into your blood and you're not getting it into your bone, you could end up with weak or wobbly bones. We saw an image of previously with disorders like rickets. Anyways, that's all on bone. Please reach out with any questions, concerns, or comments, and I will see you guys in the next one.